Okay, now I would suggest strongly that even if you think you know what you're doing at this point, don't install Eclipse. Wait till we all do it as a group, and that way you'll be able to, if you have an old version laying around, it'll still work. And you'll also make sure your environment around it matches what everybody else is doing. And it's very important. It's part of style that we all be working from the same sheet of paper and that everything be consistent. So everybody got this downloaded. Just save it in your download. Remember the name of it. So when I say we want to go get the Eclipse download, we'll know what we're talking about. When we did this should have created a file. You can go down to the right, do show in folder, find it, look at the name, remember the name or write the name down so you'll be able to find it again easily. So I'm going to close a couple of windows here. And let me see what else I got open here. I can stay open. Let's go. I'll just go back here. Okay. Now, one of the things I noticed is when you put your hand up, don't just start speaking. Wait until I call on you. Some of you got a little carried away there and you were talking on top of other people. It makes it a little hard to sort out what's going on. I don't have stereo headset. And so I can't listen to you from two separate ears. Plus, I think that would be hard to do anyway. So let's talk a little bit. Let me save this on the desktop here. There we go. Let's talk a little bit about why we're using Java to learn data structures. Okay, I mentioned one of the main reasons is because Java finds errors primarily at compile time, not runtime. Now that doesn't mean Java is the perfect language. Let's see, Java equal perfect. No. Is it a good language to learn data structures with? Yes. Why aren't we using Python? Why aren't we using JavaScript? Why aren't we using C or C++ or C#? Why aren't we using Fortran, COBOL, Visual Basic? Well, I mean, all of these programming languages have their advantage. You don't necessarily have to like one over another. There's a lot of little religious wars that people, and usually these are uninformed people, have about computer science. You know, there are people who fight the Android iPhone battle. I'll never use an iPhone. Do you hear what they did? That's Apple. I don't like Apple. They're no good. Got all these reasons why they're no good. No, Android, can't use Android. Android's sponsored by Google. Google's evil. Look at this iPhone. I can actually get 65 million colors on the screen. Well, there's a use for both. Remember, I work and have been working in computer field for years. And there's a motivating thing that says, I like what I need to like to do the contract. So if somebody comes to me What am I going to say? Oh, heck no, I'm not going to possibly be able to do that. I don't like Steve Wozniak. And he was telling Steve Jobs how to build Apple II computers and Apple I's. No, of course not. I'm going to be a computer scientist and use the tools in hand to build them what they need. Data structures will be the same way. We'll find some that, man, if we could write our own data structure, it'd be so much better than using an array list. Well, not necessarily. One of the things that we want to make sure we're thinking about all the time is clever is always bad. I can change that to say evil if you like. For anybody that comes up to you and says, oh, look at this great, clever solution I came up to this program I had to write. Well, no, that's probably going to be a terrible solution because we're always writing things for enhancement and maintenance. So I don't want or you to have to rewrite somebody else's code. If I ask you to write some code for me, you work for me, and I send you out to do something, and you come back with something that's clever and something that's stylized, I immediately have to get somebody else to write it in the correct style and to get rid of the cleverness. Now, that doesn't mean I shouldn't write something that's well written and well thought through. I should. It also doesn't mean that I shouldn't pick the right data structure. I should. But a known thing among really good computer scientists is optimization tends to make things look worse than they are. I don't need to lapse into assembly language to fix this thing when I'm only executing that line of code one time. If I'm doing something millions of times and it's performing badly, I might consider thinking about optimizing it. But otherwise, as long as I'm using the correct tools and I'm not being clever, if it get it to do what it needs to do and it's running in reasonable amount of time, I don't need to do optimization on it. And that seems to go against what in your head you'd want, well, I'm going to write this so it runs as fast as possible. That'll also write code that's very, very hard to maintain. And I don't want to pay for somebody to have to maintain code. I also don't want to assign you an assignment that says I want to turn the text from black to red and have you come back having fixed other parts of the program. That costs me money. I only want you to do what you need to do to solve the problem at hand. You might recommend that it be done, and I might later consider having it done and budget for it. But in general, I want done what I need done, and I don't want to have other things done. Now, you might say, well, that's kind of silly because when I work on this later, I'll know exactly what I need to do because I wrote it. Well, you very likely may not be the person who has to fix broken code. Just because you wrote it doesn't mean it's going to live with you forever. Hopefully, you'll move on. So keep that in mind as we talk about how we're going to model our style and how we're going to get things to look like Bastain, that's me, my code, so that it gets an A. Anytime we get into a situation where I've told you one thing and you find in a book something else, for now, I'm always right. And so we'll go with what I say until I tell you that I want you to think about it differently. I won't always give you the complete story on day one. I may let you learn part of the story as we go. And I may, as we're working on things, say, well, now that we've written it in Java, let's see what that would look like if we did it in a different language. But data structures are universal. Basically, we've got in a computer system, we have some input, we have some processing, and we have some output. It's unlikely we have processing that produces output multiple times because it would always produce the same thing. And once we've had it run once, we don't need to computerize it anymore. In the processing stage, generally, we're going to have algorithms and data based on data structures. And we're going to focus on data structures and the algorithms that support them. Not such a heavy hit here because most of the algorithms, as we learn the data structure, we'll go, oh, I kind of know how I would do that. But we'll hit the high ones. And by the time we get to the point where you're doing your projects, you'll already know how to deduce what those need to be. There are several styles of programming in vogue. In early days of programming, most everything we did was procedural. Meaning I would give every step along the way that I needed to do, very assembly language type, but written in a higher level language. Then people realized that we might be able to simplify our thinking about the code by stylizing it in something called top-down programming. In top-down programming, at my highest level, in my main level, I might have an initialization function that I call. I might have something that does the work. I might have something that does the final summarization work. And I might have something called shutdown. And then I would go think about init. What does init contain in it? Well, I'd write some methods inside of init, like establish variables, make network connection, set up security. And of course, then I would have a do it function, which I would break into parts. And as you can see, inside establish the network connection here, I might say find an available pipe. Get encryption key. Now you might go, ooh, that sounds like security. Well, but I'm going to need an encryption key if you're to attach to the secure pipe. But I could write an entire structure like a tree where I write each level describing what I need another level to do, and then give each of these nice names. You know, I've seen terrible names. For example, you might get something that was like network connection 30 or 3. And then that would be the method that gets called. Well, that's not very newsy, but it could be drawn back to this if I had a good flowchart describing what's going on. So this was another way of writing code. We could procedurally do it, or we could top-down describe the algorithm. Then we could also farm out the various levels to different groups of people to work on them. Maybe we have a group that's very good at writing security code. Maybe somebody that's very good at writing parsing code that can take data and break it into its component parts. Eventually, this became, we sometimes call this OO, object-oriented programming. Java is an object-oriented language. And in here we have different levels of OO to be done. We have an OOA, an OOD, we have an OOP. We might have these things being thought about as object-oriented design, object-oriented analysis, object-oriented programming, various levels. And each of these could be a different job description in a company. Certainly a guy that does programming is not necessarily going to be good at analysis. And an analysis guy may not be good at design because this guy probably has to talk very closely with the business unit for which the program is being developed. And so different types of jobs are developed around these. We're kind of going to be thinking about programming and analysis, but we want to keep in mind that those tasks are very different. And typically, somebody that can do programming isn't paid as much as somebody who can do his analysis, and not paid as much as somebody who can actually do design. We often think what a wonderful thing it would be to be a programmer, because we often picture this as something we're going to get to do. quite often programmers are given a sheet of paper that says, here's exactly what we need you to write. And it takes very little creativity. So you want to think about, as you're thinking about how you'll parlay the experience in this class into something that could be a job later, how you could take these things and turn them into something that could not only be interesting, but could make money. Nothing wrong with money. Now, Java in later times also realized that maybe it would be nice if they could support something called functional programming. Around about Java 8, they put some things in the language that let it start to support the idea of functional programming. And we'll look at some of those as we're working away. Of course, we'll hit a lot of its object-oriented nature as well. And we want to talk a lot about that tonight, actually, to make sure we understand what it means. So functional programming in Java introduced a couple of concepts. One is something called streams, and something called lambda expressions. And we'll talk about those on a different night, but just be aware that they are in the language, and you very well didn't get a lot of exposure to them in your previous Java classes. And if you've been working in the business, typically many people don't allow you to go here because it's not understood well in the analysis community. But it does buy us an awful lot. So we're going to kind of focus, first of all, at object-oriented programming. So before I do that, does anybody have any questions about any of the things that we've been talking about in this set of notes I wrote here? Okay. Trying to get that off the screen. Okay, so let's talk a little bit about object-oriented programming or design or analysis. I'm going to bundle it under programming for now, but it goes further than that. First of all, there are 4 primary principles that we need to know about, because they kind of define when something is correctly object-oriented and when it's not. The first one is a principle I'm going to call abstraction. We'll come back and fill this in a second. The second one is something called encapsulation. Third one is something called hierarchy. The fourth one is something called polymorphism. So what data abstraction says is that if I'm going to create an object which can hold its weight as a real object-oriented object, one of the things it needs to be able to do is to represent something tangible. That's simple, easy to meet, but we'll find that it's not always done. And so we want to make sure that what we're abstracting is something tangible. It's not just a goofus. We don't know what a goofus is, so it really is not something tangible. A student could be represented. An integer could be, a string, a linked list. Those all could turn into things for which they represent something tangible. And just as importantly, there should be able to find some natural operations that can be performed on this object. Just like it's a reasonable thing to think that if we have an integer object, we should be able to add another integer object to it. But if we have an integer object, it doesn't make a lot of sense to add a cat to it. So that probably wouldn't be a natural operation of the results of that. So when we are trying to think about what an object-oriented thing is, if it even fits as an object in our design, one of the things we want to make sure of is that we can come up with some natural operations that could be done on these. And very often those natural operations are going to be the only things we allow on our object. So we want to think it through very carefully. Objects are not to be lightly taken. They're not just little lightweight things that we can throw into a problem. We want to make sure we really understand why we're creating them. And in a language where Java tends to have everything be an object, that can be tough. Now, encapsulation, it often focuses on what I'm going to call data encapsulation. Or sometimes that's called data hiding. The idea here is that we don't want that to be visible to the outside world. It could be that we have a string, and the string internally in our program is stored in something like French. And every time we need to use it, we have to translate it back to English again so we can use it. We don't necessarily have to expose that to the outside world. The outside world might think they can give us an English string, and when they ask for it again, they get back the English string. Now, that's probably not a good example because we wouldn't do that, but that's a very possible thing. Now, another thing might be, let's say we wanted to get the latest stock price for IBM. We don't know if we're getting that from a variable inside that's stored it as a floating point number, stored it as a decimal number, an integer with a fractional part. It actually made a web services call to the Wall Street Journal to get the number. We don't care. Internally, we can store it however we want. We'll encapsulate it. And anybody that wants to get the data can have the data. Somebody who wants to change the data can potentially store the data, but they don't need to know how we're doing it. To cause this to happen, we're going to create what we're going to call accessor methods. And in our accessor methods, we're going to take and we're going to create what we would call getters and setters. I'll just call them the informal name first. Now, a getter and a setter opaquely uses our class and allows us to get at what we would typically expose as data members in other programming languages. So what I will now do is instead take my data member and consider it private to the class, meaning that nobody external to the class can see how I'm storing the data. But I will provide people that need to get the data with something we will call a getter. And if they need to change the data, something we call a setter. Now let's say that I had a private variable stored internally as an integer called grade. I might have somewhere in my program something that can return an integer, or this is public, called get grade. And inside of it, you may simply say return. You just say return grade, but something that allows me to have an opportunity to get it from any type of store that I wish and return it as an integer, which is what you're treating it as. I'm not going to finish that method at this point because we don't need it. I might also have the ability to say public returns void set grade, where I pass in an integer. And here, I'll do something that uses the G variable in order to change my internal representation of it. I might provide both, I might provide neither, and I might provide only one of the two. So my variable internally could be write only, could be read only, if I supply both, could be read and write, or it could be completely internal, meaning not available at all. Now in Java, we typically name the methods get and then the internal name that we want the property to be known as, or set, and we name it. Gets are called accessor methods specifically, just like we call the entire set. And those that can change it, we often will call mutator. Oops, that's not the right spelling there. Mutator method knows how to change something internally, which is being treated as an accessor method. An accessor also could be simply called an accessor method and would allow us to do a get. In some modern pieces of Java, you may also see a property called grade referred to simply as grade equals something. Or I might have some external way of getting something from a property which is called grade. We won't use that notation, but be aware it's there. And if we come up with a case where we need to use it, I'll say now we're going to use that other notation I told you about. For now, think of the ability for accessor methods to be getters and setters, and not specifically used in a sense where we're calling them properties. Now, hierarchy has really two major things that we want to have. One is what we call an is a relationship, and the second is something we call a has a relationship. We think of an is a relationships as being what we would think of in a programming language as inheritance. Now, inheritance means something is a something else. A dog is a animal. So there's a hierarchy here. If I were to have an animal object or interface, I could extend that or implement that with a class called a dog, and that would be an example of hierarchy showing me inheritance. A has a relationship, on the other hand, is one where we think of something being more of a containment type of expression. But we're going to reserve that word for when we're talking about containers, and instead we're going to use the word composition. or something is composed of something else. For example, a car has a spare tire. Spare tire. A car could be an object which is composed of, among other things, a spare tire. Of course, a spare tire is a tire, so we also have an example of something that could be an inherited property here. Now, composition actually comes in different flavors. And the two main flavors we would talk about are the one called composition and the one called aggregation. In composition, we always think of the object and its lifetime being tied to the object that has it. Now, yeah, I know we could stick the spare tire somewhere else and use it. And in general, it wouldn't be that debatable of what the object is. But in this case here, we're thinking of the spare tire as going away if the car goes away. So we call it a composition. If the objects were able to exist independent of each other, meaning one may aggregate the other, meaning it is a single direction relationship, we use the expression instead of has a, of part of. Still has a relationship, but we want to think of aggregation here as kind of being a special form of what we would call an association. So it's one way between me and who I'm actually pointing at or being composed of, but we can exist independently of this. The actual type, for example, where I've said they independently don't exist, we often call an association. So let's just kind of consider it this way. Compositions are made up of associations and aggregations, where an association is a little like this. Let me move it down so that it's a little closer to it. It represents has a little better. But this object here will go away where this guy goes away. He controls the lifetime. Where aggregation kind of means I'm a part of, and I can continue to exist without. So if you were a student in a class, the class might, point at a particular student. But when the class goes away and it exists the next year, that same class can exist without that student. Now, one of the problems with this is very often these definitions are sorted around. And sometimes aggregations pick up the definition of just in people's literature. So kind of go with what we talked about here. There's kind of a general has a relationship, which we'll call a composition, which has two forms, an association and an aggregation. In an aggregation, the two parts typically continue to exist, whereas in an association, one is made up of the other, and this guy controls the lifetime of that guy. And that will give you a good enough sense of how hierarchy will work when we start talking about the relationships in other ways. And the last one is a little more complicated to talk about. because there's examples in the literature which will confuse you tremendously. Polymorphism, if you look at it, has the word poly in it, which means many, and morphism, which means body. And what it says is that if I have a collection of objects and they're collected at some parental level, I'll explain this in a minute, they will nevertheless behave correctly. Now, let me give you the confusing part, first of all, and then explain what I'm talking about. I have a class or interface called animal. I'm going to extend that class to a class called dog and a class called cat. I'm not going to extend dog, but I'm going to extend cat to contain a house cat, a lion, and many other things. But those are the ones I'm going to talk about. Now, I'm going to ask each one to speak in a second. What should a dog say when it speaks? Something like bow wow? What should a cat say? Raise your hand if you think you have an idea. Kyle, what should a cat say?
Meow.
Okay, that'd be a possible thing for a cat to say. Now, what should a house cat say? Oops. John, what should a house cat say?
Hiss.
Hiss, okay.
We're going to tell them jokes.
And Ebony, what should a lion say?
Roar.
Roar, I like roar. Okay. Okay, let's for the second pretend like our house cat's not mad at us. I do like hiss, but we'll let him go ahead and say the same as a regular cat would say. What should an animal say? Samir?
Grr.
A snake would say grr?
Perhaps.
Well, the real kind of thing is we could come up with something possible, which is a universal animal noise, but also maybe it says there is nothing that it's going to say. And we make this guy what we call abstract, meaning he can't be implemented directly because there's methods that he has that aren't implemented. But we could create any of these other things, except we've decided we can't create a cat either. But we can create a house cat or a lion. So somewhere I'm going to say, I have a thing called dog, which I've temporarily called dog, is equal to a new dog. And then I'm going to have a line that says dog.speak. And we're going to hear bow wow. And somebody tries to create a cat that doesn't work, but they decide they're going to create a house cat. It's spelled the same way. And they say hc.speak. And it says meow. Now, it would be perfectly legitimate to create a cat called HC, which is a new house cat, and say HC.speak, because it'll automatically look up its tree and find the right thing. Now, if cat didn't have anything to say, then animal. Notice that I can create a cat as a name. I just can't create an instance of one. So I can't do a new one, but I can establish it as the actual interface that I'm going to use. So this is all well and good, but nowhere here, I've demonstrated just using it correctly, not correctly, but as it makes sense. A dog is a dog, so when you call it, it should say bow wow. I did a cat as a house cat, which we called as an interface of a cat. First case, it went up and it found the correct thing to say. And in this case, it automatically finds the correct thing to say. If I try to do this, it won't work. Because even though a house cat is a cat, which is an animal did not define a method for speak. But still nowhere here have we touched upon polymorphism. Percy, you have something?
Yes, I was wondering if it would still work if you used house cat.
Yes, you use house cat, which was the first case we did here. House cat will work because house cat doesn't have a method to speak, but if it goes up its tree, it is a cat, and the cat knows how to speak. But none of this really exhibits polymorphism yet. What would exhibit polymorphism would be if we had created an array of animal. Where am I typing? I'm typing somewhere and don't see it. Okay, so I'll create an animal array called animal array. And it's equal to, and in here, I'm just going to put a new dog, a new house cat, a new cat, a new lion. Then I'm going to go through and take my array. I don't want to show you that right now. So we'll pretend like we've got each one, but I'm going to say A sub 0 dot speak. What do we have? We have 1, 2, 3, 4. So we need 2 more of these guys. This guy is going to say bow wow. This guy is going to say meow. This guy is going to say meow. This guy's going to say roar. Try using the sprite names up there. I did. Oh, those look like peas, not O's. Yeah. Dog that can't talk. This is an example of polymorphism. This is not. This is just simple inheritance in action. This down here, we've taken a particular thing which can contain all of these. We've iterated through it, calling speak upon it. It has a abstract speak method for which all the others have inherited. And when they're called, the correct thing happens. This is an example of polymorphism. And we're tipped off to it because we have multiple things inheriting from the same thing, but then treated as though they're from the same container. Now, this may have some syntax errors in Java. I'm not going to guarantee I typed everything correctly. But that's the general idea of the fourth thing we need to have. So our 4 items in review are we have abstraction, meaning that we need something tangible to represent as an object. And it specifically needs to have natural operations we can put upon it. So our animal naturally could speak. Encapsulation, which says it's okay to hide our variables. And in fact, normally we also want to hide our implementation, although that's not always mentioned under encapsulation. We can mention it there. Implementation shouldn't be made public, normally. Hierarchy of is and has, we have the idea of inheritance, which means I am something. And we have the idea of I have something, or something is a part of me. And then polymorphism, which says that if I happen to have a collection of objects, but we're not using them at the level for which they were instantiated, we're using them at a parent level, we'll get correct behavior if we do that. Any questions about those particular pieces of the discussion? Okay. These will tend to apply with Java, but they're very general that I'm getting ready to talk about. Oh, I'm in the wrong part of my lecture. Interface. An interface in object-oriented programming is a contract between a set of methods and objects. The contract is signed eventually when somebody implements the interface. So it's a contract which is signed by its implementation. Now in Java, up until Java 8, interfaces were pure abstractions. In Java 8 and beyond, interfaces may include things called default methods, which can be overridden. Spelled right? I don't know. I'm not going to look it up. And it can also have static methods, which can't be overridden. Anything that's not a default method or a static method is the original interface contract. And no indication or just standard contract. And if there is only one, the interface is a candidate for being what we call a functional interface. Won't always be one, but it's a candidate for being one. Now, because of the way Java uses these, an interface can extend, I'm going to just use the non-keyword, extend other interfaces. Notice that that's plural. Now, a class can extend other classes. No, I'm sorry, and other. And possibly implement many interfaces. Classes that are not abstract can be implemented, or should be instantiated. So what that says very simply is, in order to avoid something that is called multiple inheritance, things that can be instantiated, which are classes, are allowed to only implement, or I shouldn't say implement, extend one other class, which of course itself could extend another class, which could extend another class. But any class can implement many interfaces, because interfaces don't have any implementation inside their, or it's this guy, their standard contract. Now, they might have implementation inside a default method, and there's some messiness that goes on with implementing or overriding those. But since static methods there can't be overridden, that doesn't turn into being a problem. We'll have to look at some classes to see where that matters later. But in general, in order to be an instance of something, and that's a term we'll use a lot, you have to have been an instantiable class and then instantiated. So if I have a class called student, call it student here. I know some things about this. Number one, in most cases, this will be a class that follows. There's cases where I'm going to write the class in line so I can use an interface name here. But in general, this will be a class name, an instantiable class. In any event, if I use new on it, whatever this is, has to be instantiable. I'm going to instantiate it into a variable called student, which is of type or class student. Now, I don't know anything about student, the class, except for I do know, because of principle one, there's going to be some type of operations that I can do on it, which are legal. Now, a better way to do this is to have an interface called iStudent, for which I'm going to create a student instance as a new student. Notice this is a class, this is an interface. That way, if later on I create myself a new smart student, which is also a class, it still is an instance of an iStudent. So this way I can vary my implementation independently of the interface I'm using. So I can write an entire use of an iStudent with a contract for an iStudent, knowing that somewhere somebody's going to instantiate either a student, a smart student, a dumb student, a new student, whatever it is, and they are required to implement this interface. If I do it this way, then I'd have to create a new smart student who happened to be a smart student, and I couldn't take advantage of this interface being usable. It also allows me to give you, for example, an I linked list where you create a new linked list, which goes with my I linked list. And then I can keep changing these and test everybody's code to make sure it really supports the correct interface. And in our next class, we'll, of course, start really digging in to talk about that as we start working on classes and interfaces. Now, the staticness of this, and also we can create classes which are purely static. Allow me also to create classes which just kind of contain a bunch of methods which are usable without having a specific instance having to, be the one we're doing it on. It doesn't mean they won't be used internally as things, but we'll also see that a static class turns out to be something that's kind of useful. So does anybody have any questions about the differences between interfaces and classes and instances of classes? Xavier?
So you mentioned that you can use multiple interfaces when instantiating a class.
Right.
So what would happen if you have multiple methods of the same name?
That can't be a problem if you're using multiple interfaces, because remember, there's no implementation of those. So in an interface for the standard methods, let's say to a meta display method, whatever one you implemented would satisfy both's ability to have that method. Where that becomes a problem is if they're default methods. And we'll talk about the way around that. They are truly a problem.
Okay.
They get you into the same problem you'd have had if they implemented multiple interface in the first place. Any other questions? That was a good question.
I had a question, Professor.
Sure.
What Xavier just mentioned, does that have to do, are we going to discuss the relationship between that and overload? Because that kind of confuses, my understanding of it, because I know that overloading is basically multiple things you can do from the same method. It's like the same thing.
Right. It's very, very similar to that. Usually it's overloading a method because of the fact that you have different parameters being passed in. And we'll talk about that.
Okay, thank you.
Anybody else have any questions? So we've installed Java. Java works inside the console. Double check that. If it hasn't, you're going to find somebody else in the class and work with them to get your version working. On Wednesday, we're on Monday, Wednesday class. So on Wednesday night, we'll get Eclipse working with the Java. And there's a couple steps that we have to do that are a little out of what you would normally do if you were just following the directions. They're really simple and they make a lot of sense, but that's why I don't want you to just go ahead and install it, because then you might have to uninstall and that can get messy. But if we do it the way that we're planning on having it done, when you're finished with that, we'll have a workable Eclipse. We'll have an environment in which we can actually test our Java code as we go along and then start introducing data structures as they become appropriate. I need to teach you how to program like me first. And so we'll have a couple sessions where we do that, and you'll have some programming assignments to get that done. There's some very specific things I need to see in your code so that if you ever work for me, I don't have to fire you because I'm paying extra money to support your style. And so we want to make sure that everybody's on the same sheet of paper when we do it. And it may involve you having to do some things that you're not comfortable with in your style. You can always go back to your old style after the class. But while you're in this class, you have to do it my way. And I know that sounds kind of, but I have a long, long history of very, very successful people. And I want to make you be some of those moving forward. And I see no reason not. I haven't really seen anybody, that raised their hand and, asked me, some really, really out there type of question. Everybody was on point. You will be graded on participation. When I ask if there's questions, that doesn't mean you immediately have to. But if you have one, it's a good opportunity to ask it and be counted. I do know who's here the entire session. I do know who's not sitting at your terminal because of various things I know about how the question things with the little green dots do. And, I ask that you participate as fully as possible and give the class a shot, even if you're one of those people that normally wouldn't do that. You would think it was cool to diss the class. Don't do that. Okay, well, we have gotten to 9:50, which is shutdown time. So I will see you folks on time and ready to go. Make sure you've got Java installed and that you've reviewed your notes before class on Wednesday. So you guys, what we do normally is right as you leave, turn on your microphone and say goodbye to me, and I'll see you people on Wednesday night.
All right. Thank you, Professor.
Yeah,
Thank you.
Good night.
Professor. Good night.
Good night. Have a good night.
Good night. Bye-bye.
Professor.
Good night, Professor. Thank you.
Good night. Bye-bye. See you on Wednesday.